The modern electrical grid operates on a strict physical mandate. Energy must be consumed at the exact millisecond it is generated. To maintain system equilibrium, supply and demand must perfectly match at every moment. For over a century, this equilibrium was enforced by massive physical weight. Thermal power plants generate electricity using giant, heavy rotors spinning at constant speeds. These spinning behemoths possess immense kinetic energy. When electrical demand suddenly spikes, their sheer physical momentum acts as a shock absorber, naturally resisting any sudden drops in the grid's operating frequency. Engineers call this physical inertia. Modern renewable sources, like solar panels and wind turbines, lack this heavy rotating mass. Transitioning to these intermittent technologies removes the grid's natural physical shock absorbers. Without that physical momentum, the system is highly exposed. If power generation drops abruptly, the grid's alternating current frequency begins to fall away from its required 60 Hz baseline. This is a conceptual representation of that standard 60 Hz sine wave. Even a micro deviation, dropping just a fraction of a hertz, forces automated safety breakers on generators to trip offline in self-defense. This can trigger a cascading failure, leading to total infrastructure collapse and regional blackouts. When a sudden spike in evening demand outpaces the intermittent supply from a dying wind breeze, the frequency drops and the wave distorts. The grid can destabilize in a matter of seconds. Stabilizing a decentralized grid shifts the burden from generation to storage, necessitating a multi-scalar physical response to maintain equilibrium. The foundation of modern grid stabilization starts at the microscopic level, with the lithium-ion cell. These cells do not hold electricity directly. They utilize reversible redox reactions to temporarily store electrical energy as chemical potential energy, locking it in place until the grid demands it. This cross-section reveals the physical architecture of the cell: two solid electrodes separated by an ionically conductive but electronically insulating liquid electrolyte. During the discharge state, positively charged lithium ions delithiate from one electrode. They migrate directly through the liquid separator layer to reach the opposite side. Because the separator physically blocks electrons, this internal chemical migration forces negatively charged electrons to travel out through the external circuit. This movement performs the usable electrical work. The exact roles of the electrodes depend on the state of the cell. The definitions of anode and cathode actually reverse depending on whether the system is charging or discharging. This process exacts a physical toll. Constantly shuttling ions back and forth stresses the internal crystal structure of the electrode materials, eventually limiting the overall cycle lifespan of the cell. To be useful for grid-scale stability, millions of these fragile, microscopic chemical reactions must be perfectly coordinated and insulated from the risk of thermal runaway. At this scale, the battery system functions as a highly integrated electromechanical transducer, governed by extreme precision control. Scaling up from the individual cell brings us to the macro infrastructure of a utility-scale battery energy storage system, commonly known as a BESS. These systems are deployed in modular, containerized units, each housing thousands of individual battery cells operating in tandem. Managing this massive volume of stored chemical potential requires a strict three-layer control hierarchy to successfully translate chemical energy into actionable grid stability. The foundational safety layer is the Battery Management System, or BMS. It constantly monitors temperature, current, and voltage to keep every cell strictly within a safe operating area. Above the BMS sits the operational hardware layer, the Power Conversion System, or PCS. This contains the crucial bidirectional inverters that bridge the DC power of the batteries to the AC power of the grid. This is where raw direct current is rapidly toggled and shifted to match the high-voltage alternating current required by local transmission lines. Operating on the grid, the PCS acts as synthetic inertia. It can inject massive amounts of AC power in milliseconds to correct dangerous micro-deviations in frequency. This millisecond response time stands in stark contrast to traditional spinning reserves or automatic generation control, which require minutes to physically throttle up generation. Finally, the strategic software layer is the Energy Management System, or EMS. This high-level coordinator receives signals from the grid operator and dictates exactly when to charge or discharge. The EMS executes a strategy known as value stacking. It deploys the BESS to provide multiple distinct grid services simultaneously, maximizing the financial return on the hardware. One primary EMS application is peak shaving. The system discharges stored energy to momentarily reduce total grid power consumption during high-demand daily windows. This document details how discharging a behind-the-meter BESS system smooths out the highest spikes in a commercial consumer's overall electricity profile. The underlying economic incentive for peak shaving is clear. It protects industrial consumers from massive demand charges levied by utility companies during periods of grid stress. The three-tier BESS architecture successfully replaces the slow physical mass of traditional fossil fuel generators with instantaneous software-driven synthetic inertia. Electrochemical storage is highly effective for sub-second and hourly responses, but grid networks also require instantaneous microbursts of energy alongside massive long-duration reserves. This graph maps the analytical framework engineers use to classify storage technologies, plotting specific power on the y-axis against specific energy, or total duration, on the x-axis. Lithium-ion battery systems occupy the middle ground. They offer highly balanced operational metrics for both moderate power output and moderate discharge duration, but the grid requires extreme solutions. Engineers need technologies that plot extremely high on power output and others that stretch far out on total duration. For microsecond frequency regulation, the primary kinetic solution is the mechanical flywheel system. Flywheels utilize highly engineered mechanical hardware designed to operate with near-zero friction. The mechanism stores kinetic energy by suspending a rapidly spinning mass inside a strict vacuum enclosure, using magnetic bearings to eliminate physical resistance. The specific advantage of a flywheel over a BESS is its sheer durability. It can absorb and discharge massive power spikes indefinitely without suffering the chemical degradation that limits battery lifespans. At the opposite extreme of the energy storage spectrum sits pumped storage hydropower, the technology that currently dominates global bulk energy storage. Facilitating pumped hydro requires massive infrastructure scaling and highly specific geographic elevations. Its thermodynamic cycle relies on using excess midday solar power to pump water uphill. This effectively converts baseline electrical energy into massive stored reserves of gravitational potential energy. Matching these physical mechanisms, electrochemical, kinetic, or gravitational, to specific grid timescales creates the layering necessary for continuous system stability. We can observe how these technological modalities operate together by deconstructing their orchestrated sequential response to a sudden catastrophic drop in renewable grid generation. In the very first millisecond of the event, mechanical flywheels instantly dump their kinetic energy to catch the immediate frequency collapse, stabilizing the line before automated breakers can trip. Over the next several seconds, the best power conversion system takes over. It injects sustained synthetic inertia, successfully bridging the gap while thermal plants attempt to ramp up. In the critical hours that follow the initial event, pumped hydro valves open. They release their gravitational potential, sustaining the macrogrid through the entire high-demand evening peak. There is no single perfect energy storage solution. Grid resilience requires a highly diverse, interconnected ecosystem of varying physical architectures. As the scale of decentralized power grows across transmission networks, this mechanical orchestration dictates whether the system holds or collapses. Achieving true net-zero stability depends on the masterful orchestration of these chemical, kinetic, and gravitational forces.